Hello everyone. Today I would like to talk about GestaltMatcher, which is an artificial intelligence used within the PDA study. I have nothing to disclose. I would like to start with a question many of us know when we have family. Does Victor, one of my brother's twins, look more like his father or his mother? If I were to do a poll, it could be that there is a slight trend towards the mother. However, what does it mean? First, objectifying similarity is not trivial. And second, the question may not be well posed after all if it cannot be answered unambiguously. If I were to ask about the eyebrows, for example, significantly more of us would probably agree that Victor got them from his mother. The fact that certain phenotypic features of the facial gestalt are inheritable is also the basis of syndromology. For example, many of us learned to recognize a distinct shape of the eyebrows in patients with mutations in KMT2D, and we have named the entire disorder after this finding to teach each other. For the other two syndromes, probably fewer of us could name the right diagnosis. However, is this because it is a less recognizable or distinct facial gestalt, or because less of us learned to recognize it? I will try to answer this question for two artificial intelligences that I know quite well. One is called Deep Gestalt and has been described in the literature 2 years ago, and the other is a further development of Deep Gestalt, and we call it GestaltMatcher. This will also be the main topic of my talk. Look at the performance of Deep Gestalt, which is the default algorithm within Face2Gene, on the test cases with Kabuki and Mabry syndrome. The Gestalt score that is achieved for the correct diagnosis is very high and brings it to the top of the list. For the third disorder, however, we do not see such a high Gestalt score for the suggested diagnosis on the top rank, although there are certain features that would fit. The micrognathia, for example, is also a feature in Wolff-Hirschhorn syndrome. However, the correct diagnosis is not in the list of syndromes this AI can recognize. Let's now have a look at a more comprehensive list of syndromes that Deep Gestalt can and cannot recognize with sufficient accuracy. We ordered all diseases by the number of cases that had been submitted to ClinVar. For KMT2D, we counted 292 pathogenic mutations that cause Kabuki makeup syndrome. This compares to 14 cases with PIKV, a Mabry syndrome disease gene. All the syndromes that are ABValid are on the left, and for LEMD2, the disease-causing gene of the third test case, there were just too little data to learn this phenotype. Likewise, in ClinVar, there are only 2 submissions so far. We can therefore take ClinVar submissions as a proxy for prevalence and state that Deep Gestalt does not support ultra-rare disorders. This certainly is a big issue, as most of the syndromes we now know are ultra-rare. Thus, our motivation is clear. We need an AI that can match a characteristic phenotype, even if there is just a second patient of its kind. Let's recapitulate the challenges for artificial intelligence. Deep learning is well suited for big data. Relatively small data sets are therefore an issue, particularly if the phenotypic variation within a syndrome is high. And third, the interpretation of the performance of an AI requires an understanding of the complexity of the problem. The diseases that we intend to differentiate are often referred to as classes. However, how many are there actually? Should we train for phenotypic series? Should we define each gene as a separate class? What about pleiotropy? One strategy to tackle the issue with small datasets is to identify first a similar problem where images are not the bottleneck. This is the case for intra-person verification. Deep convolutional neural networks that have been trained on portraits that are publicly available are built in many of our smartphones. The CNN decides whether to unlock the phone when you look into the camera. Syndrome identification is a similar problem where we have to decide whether a portrait fits to a group of similar patients. We can therefore use an AI that was trained to recognize celebrities. Here you can see a typical architecture of a deep neural network with many layers for pooling and convolution. For deep Gestalt, we extended such a network architecture by an additional layer which contains all the syndromes that this AI can distinguish. That is roughly 300 disorders, and on the test set of the London Dysmorphology database, we achieved a top 10 accuracy of more than 90%. That means in more than 9 out of 10 cases, the correct diagnosis was amongst the 10 differential diagnoses that Deep Gestalt suggested. Some of you know the London Dysmorphology database as a reference tool, but its size is too small for training an AI. I'm therefore very happy to announce today the release of GestaltMatcher database. It's a software framework that enables the community to annotate medical imaging data from the scientific literature in such a way that it is usable for deep learning. Thus, it's a great resource for anyone interested in building his or her own AI for dysmorphology. Clinicians may also use it and should think about it as the Pinterest version of OMIM. While GestaltMatcher currently contains around 10,000 cases, we got access to even more data via a collaboration with FDNA, which is providing its services via the app Face2Gene. More data means that we will be able to solve a few more diseases with the classical approach from Deep Gestalt. But it's not a remedy for the problem, find the second patient of its kind. What we want to do. We would like to search with a portrait image for another matching case, not a disease. We therefore need a space in which we can place a portrait of a dysmorphic individual. This is done by processing the image through a CNN that is pre-trained on disorders. We use the values computed for the penultimate layer, which is the feature layer. This is a facial phenotypic descriptor, or also a coordinate which defines a position in a clinical phase phenotype space. Any point in this CFPS is an image, and the distance between cases are a measure for the similarity. Remember, the similarity that we are interested in is syndromic similarity, not family or ethnic similarity. This table shows how much the performance for matching patients with the same disease gene improves when we work in the clinical phase phenotype space rather than a space that is just defined on normal faces. The top 1 matching accuracy roughly doubles no matter whether we work on known syndromes that are already app-valid, such as Kabuki makeup syndrome, or frequent syndromes with less characteristic facial gestalt, such as Turner syndrome. The target set contains all the ultra-rare disorders, which I will go into more detail in a minute. Let's first revisit distinctiveness or recognizability. Here, measured by the top 10 accuracy that GestaltMatcher achieves. On the x-axis, we used here another estimator for prevalence, which is data from OrphaNet. Depicted here is a random subset of 50 OMIM disorders. Some of them are named on the left and colored. But the overall message here is there is no correlation. Totally different story if we ask human syndromologists to rank the distinctiveness. Higher scores mean higher recognizability according to these experts. In contrast to the previous plot, here we can see a clear correlation between human and artificial intelligence. We now wondered how many of the disease genes that had been identified with the help of GestaltMatcher and that for which the corresponding facial phenotype was described as dysmorphic could also have been matched by our approach. This is how we defined the target set of ultra-rare disorders, and now let's take TMEM94 as an example in the next slide. Biallelic truncating variants are also associated with neurodevelopmental delay, congenital heart defects, and distinct facial dysmorphism, as published about 2 years ago.